Hello student, good morning. I am Dr. Sinha, Professor of Chemistry. Today I am going to continue from the last class. Last class I have discussed group 16 elements. Introduction I have given. Now I am going to tell about electronic configuration, atomic and ionic radii, ionization enthalpy, electron gain enthalpy and electronegativity. First, I will discuss electronic configuration. The elements of group 16 have 6 electrons in the outermost shell and have ns2 np4 general electronic configuration. Now I am telling you about atomic and ionic radii. Due to increase in the number of cells, atomic and ionic radii increases from top to bottom in the group. The size of oxygen atom is, however, exceptionally small. Now, ionization enthalpy. Ionization enthalpy decreases down the group. It is due to increase in size. However, the elements of this group have lower ionization enthalpy. Elements of this group have lower ionization enthalpy compared to those of group 15 in the corresponding periods. This is due to the fact that group 15 elements have extra stable half-filled p orbitals electronic configuration. This is due to fact that group 15 elements have extra stable half-filled p orbitals electronic configuration. Now I am going to tell about the electron gain enthalpy. Because of the compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. Listen again. Because of compact nature of oxygen atom, it has less negative electron gain enthalpy than sulfur. However, from sulfur onward, the value again becomes less negative up to polonium. Now come to the electronegativity. Next to fluorine, oxygen has the highest electronegativity values amongst the elements. Actually, in a whole periodic table, fluorine has highest electronegative. And next to fluorine, oxygen has the highest electronegativity value amongst the elements. Within the group, electronegativity decreases with an increase in atomic number. This implies that metallic character increases from oxygen to polonium. This I have discussed about the properties, physical properties. Now one question is there. I want to answer that question. Question is, elements of group 16 generally show lower values of first ionization enthalpy compared to the corresponding periods of group 15. Why? Again question I am reading. Elements of group 16 generally show lower value of first ionization enthalpy compared to corresponding period of group 15. Why? Now I am giving explanation. Due to extra stable half-filled p orbitals, electronic configuration of group 15 elements, larger amount of energy is required to remove electrons compared to group 16 elements. This is the main reason. Again I am telling you, due to extra stable half-filled p orbitals, electronic configuration of group 15 elements, larger amount of energy is required to remove electrons compared to group 16 elements. Now other physical properties I am telling you. Oxygen and sulfur, actually in group 16 elements I am telling you that oxygen and sulfur are non-metals. Selenium and tellurium are metalloids, whereas polonium is a metal. Again you listen. Among 16 group elements, oxygen and sulfur are non-metals. Selenium and tellurium are metalloids. Question is asked. Selenium and tellurium are metalloids, whereas polonium is a metal. Polonium is a radioactive metal. Polonium, okay, PO, is a radioactive and is short-lived. Half-life period is very small. Half-life is 13.8 days only. 13.8 days only. All these elements of group 16 exhibit allotropy. The melting and boiling points increases with an increase in atomic number down the group. Again I am repeating, the melting and boiling points increases with an increase in atomic number down the group. The large difference between the melting and boiling points of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as a diatomic molecule, O2, 2O are there, O2, whereas sulfur exists as polyatomic molecules, S8. That's why this melting point and boiling points are more. This is the main reason. Okay. And here first point is that all these elements exhibit allotropy. Melting point and boiling point increases with an increase in atomic number down the group. The large difference between the melting point and boiling point of oxygen and sulfur may be explained on the basis of their atomicity. Oxygen exists as a diatomic molecule, O2, whereas sulfur exhibits as a polyatomic molecule, S8. Now I am going to discuss chemical properties of group 16 elements. First, oxygen states. Oxidation states and trends in chemical reactivity. First, I will discuss chemical properties on the basis of oxidation state. That is, oxidation states and trends in chemical reactivity. The elements of group 16 exhibit a number of oxidation states. The stability of -2 oxidation state decreases down the group. Polonium hardly show -2 oxidation state. Since electronegativity of oxygen is very high, it shows only negative oxidation state as -2, okay, except in case of OF2. Oxygen shows -2, but exception is there. In case of OF2, it is different. In case of OF2, where its oxidation state is +2, question is asked. OF2, you know that fluorine has -1, then 2 fluorine is there, then 2 negative means oxygen will have 2 positive. OF2, in this oxygen has +2 oxidation state, correct, because fluorine has -1, then 2 fluorine is there, then -2, then oxygen will have +2, only then it will neutralize. Then in this case, in case of OF2, oxidation state of oxygen is +2. This is exceptional question, always it is asked. Other elements of the group exhibit +2, +4, +6 oxidation state, but +4 and +6 are more common. Out of +2, +4, +6, +4 and +6 are more common. This +4 and +6 are more common. Now what about this sulfur and selenium? Sulfur, selenium and tellurium usually show +4 oxidation state. Always remember, sulfur, selenium and tellurium, Te. Selenium, you know, Se, sulfur, S. Okay, then sulfur, selenium, that is Se, tellurium, Te, usually show +4 oxidation state in their compounds with oxygen, and +6 with fluorine. With oxygen, it will show +4. Sulfur, selenium and tellurium usually shows +4 oxidation state in their compounds with oxygen, and +6 with fluorine. The stability of +6 oxidation state decreases down the group, and stability of +4 oxidation state increases due to inert pair effect. Again, you listen carefully. The stability of +6 oxidation state decreases down the group, and stability of +4 oxidation state increases. This is due to inert pair effect. Bonding in +4 and +6 oxidation state is primarily covalent. This I have told. Now I am talking about anomalous behavior of oxygen. All anomalous behaviors are important. Okay, questions are asked. And now I am going to discuss anomalous behavior of oxygen. The anomalous behavior of oxygen, like other members of P block present in second period, is due to a small size and high electronegativity. This is the main reason. Anomalous behavior of oxygen, like other member of P block elements present in second period, is due to its small size and high electronegativity. One typical example of effect of a small size and high electronegativity is the presence of a strong hydrogen bonding in H2O, which is not found in H2S. A strong hydrogen bonding is found only in H2O, not in H2S. Otherwise, you can say like H2O, there is a ocean seas due to hydrogen bonding of, you can say, oxygen. H2O has in H2O H and O. H is most electropositive, oxygen is most electronegative. Then due to this electronegativity property, they form liquid, and it forms ocean. This is the, can say, see the importance of hydrogen bonding. Due to hydrogen bonding, ocean, sea, or a river or a pond, you can say, exist. Correct? Ocean exists due to hydrogen bonding. Ocean, sea, ponds, rivers. And there is no ocean, no sea, no rivers of H2S. It is due to oxygen is more electronegative than sulfur. Oxygen is less electronegative, oxygen is more electronegative. That's why oxygen forms hydrogen bonding. But sulfur is very less electronegative. That's why it does not form hydrogen bonding. Otherwise, just like water, H2O, H2S would have existed, but it is not like that, because sulfur is not too much, very less electronegative, not like water, not like oxygen. Oxygen is very, very electronegative element. This is the important things I told you. Other things I am telling you. The absence of d orbital in oxygen limits its covalency to 4. The absence of d orbitals in oxygen limits its covalency to 4, and in practice rarely exceeds 2. Generally it will be 2, but maximum 4 for oxygen. On the other hand, in case of you can say other elements of the group, the valence shell can be expanded and covalency exceeds 4. In other elements covalency exceeds 4, maybe 6. Okay. Now I am going to discuss reactivity with hydrogen. First chemical properties, reactivity with hydrogen. All the elements of group 16 form hydrides of the type H2E, capital E. E means element. As for example, E is equal to O means oxygen, sulfur, selenium, tellurium, polonium. Okay, E is equal to O, S, Se, Te, Po. Then it forms a hydride of the type H2E. E is in general. Okay, just like H2O. If E is equal to O, then H2O. If E is equal to S, then H2S. If E is equal to Se, then H2Se. If E is equal to Te, then H2Te. If E is equal to Po, then H2Po. All are hydrides of oxygen, sulfur, selenium, tellurium, polonium. Some properties of hydrides I will discuss especially. Okay. Now other properties I am telling you. Acidic character. Their acidic character increases from H2O to H2Te. Okay, acidic character increases from H2O to H2 Te, tellurium. The increase in acidic character can be explained in terms of decrease in bond enthalpy, means bond can break easily. For this bond can break easily. Okay, then in terms of decrease in bond enthalpy, we can explain the reasoning. Increase in acidic character can be explained in terms of decrease in bond enthalpy, means bond can be broken easily. Then here, but down the group I am talking about, down the group, owing to the decrease in bond energy, owing to that decrease in bond, that is bond between H and E, E means element, okay, H and E bond down the group, okay, owing to the decrease in bond energy, dissociation enthalpies down the groups, the thermal stability of hydrides also decreases. This is the important point. This down the group I am talking about, owing to decrease in bond energy or bond dissociation in enthalpy down the group, the thermal stability of hydrides also decreases from H2O to H2PO, polonium. All the hydrides except water possesses reducing properties. This is very, very important. All the hydrides except water possesses reducing properties, and this character increases from H2S to H2Te, means from sulfur to tellurium. Oxygen is only an exception. Okay. Then this I told you that about the thermal stability. All the hydrides except water, means H2O. All the hydrides except H2O possesses reducing properties. Correct? And H2O has oxidizing properties. Then this is exception. Question is asked. All the hydrides except water possesses reducing properties, and this character increases from H2S, means sulfur, to H2Te, means tellurium hydride. Okay. Now I will tell a little more about the hydrides of group 16 elements. Special properties of hydrides of group 16 elements. Melting point, first I will tell. Melting point in case of H2O is 273, and for H2S 188, and H2Se, hydride of selenium 208, and hydride of tellurium 222. And boiling point, then boiling point of H2O is 373, 273 plus 100, 373 Kelvin, all are in Kelvin. And sulfide for this H2S, hydride of sulfur, it is 213, and for H2Se, selenium hydride 232, and tellurium hydride 269. Correct? And bond distance means H and E bond. H and E means element. Then H and E distance in picometer I am talking about. For H2O it is a 96 picometer, means less than H2S. Here it is 134, and in selenium it is further more, 146, and tellurium hydride further it is more, 169. And angle, if you talk about the HEH angle, E is the element, just like H2O, HOH angle, HOH angle, like that way with other elements. Then HEH angle in degree centigrade I am talking about. In case of water means H2O, it is 104. In case of H2S, it is 92, means less. And in H2SE, it is further less, 91, 1 degree less. And in H2TE, it is 90. Okay. And what is the heat of formation? In kilojoule per mole, heat of formation. Then in case of H2O, it is minus 286. Minus 286. And in H2S, it is minus 20 only. Means very less, minus 286 is very less, minus 286 kilojoule per mole in case of H2O. But in case of H2SE, means hydrogen sulfide, it is a minus 20. In case of selenium hydride, it is a positive 73. And in case of tellurium hydride, it is 100. Okay. Now, what is the dissociation energy? Dissociation energy, kilojoule per mole. In term of kilojoule per mole, dissociation energy. Then water has 463, highest 463, and H2S 347, less. And this selenium hydride 276, further less. And least is tellurium hydride 238. Okay. Then this I have discussed about the these things, bond dissociation energy. Now dissociation constant, okay, at 298 Kelvin in aqueous solution I am talking about. Dissociation constant at 298 Kelvin in aqueous solution for water is 1.8 into 10 to the power minus 16. 1.8 into 10 to the power minus 16. And in case of H2S, it is more, 1.3 into 10 to the power minus 7. Minus 16 is less. Okay. Minus 7 is more. And in case of selenium hydride, it is again further more, 1.3 into 10 to the power minus 4. Okay. And in case of tellurium hydride, it is further more, 2.3 into 10 to the power minus 3. Now I am going to tell reactivity with oxygen. Reactivity with oxygen. Then all these elements form oxides of the type EO2. Okay. All these elements of group 16 I am talking about form oxides of the EO2. E means element. EO2 and EO3. Two types of oxide it forms. EO2 and EO3, where E is the element. Where here E is equal to S and selenium, Se, Te and PO. Okay. Here E is equal to sulfur, selenium, tellurium or polonium. Ozone, oxygen, it forms ozone. Ozone O3 and sulfur dioxide SO2 are gases. Remember all the things. Ozone is gas, you already know. O3 and sulfur dioxide is also gas, you know. While selenium dioxide, SeO2, question is asked, what about SeO2, whether it is solid, liquid, gas? Then it is a solid, don't forget. Selenium oxide is solid. And again other important things, reducing properties of dioxide. Reducing property, who can reduce means give electron. The reducing properties of dioxide decreases from SO2 to TeO2. Okay, sulfur dioxide to tellurium dioxide decreases. Reducing properties, oxidizing properties, reducing properties. Oxidizing properties means what? It will oxidize, means say it will lose electron. Correct? It will oxidize, it will lose the electron, oxidation process. And reduction properties, it will take the electron. Then oxidizing properties means element which can oxidize, means that element will take the electron and other element will lose the electron. Correct? Then reducing properties, reverse of this. Reduction, gain of electron. Then who will give the electron? That is called reducing agent. Then here in that way you think reducing properties of dioxide decreases from SO2 to TeO2, tellurium oxide. SO2 is reducing. Again you remember, SO2 is reducing while TeO2 is an oxidizing agent. Selenium is this SO2, sulfur dioxide, is a reducing agent. Reducing agent means it will this things due to this element, you can say other element will lose the distance. Reducing I am talking about. Reducing agent, oxidizing agent means reducing agent, it will supply the electron. It will supply the electron during reduction. During reduction, it will give electron to the other will take the electron. Okay, that's why it is a reducing properties. And tellurium oxide is TeO2 is an oxidizing agent, means due to this it will accept the electron and other will lose the electron. Correct? Other will lose the electron. But in case of reducing agent was losing the electron and other was taking the electron. But here oxidizing agent, reverse case. This TeO2 will take the electron, other will lose the electron. Other will lose the electron, but in reducing agent, that other will lose the electron and just this and other element, one will lose, other will take. Okay, then this I told about the EO2 type. Now EO3 type. Besides EO2 type, sulfur, selenium and tellurium also form EO3 type oxides like SO3, SeO3, TeO3, tellurium oxide, selenium oxide, sulfur trioxide. Both type of oxides means EO2 and EO3 are acidic in nature. Don't forget, question is asked. EO2 and EO3 type, both types of oxides are acidic in nature, means it can take the electron. Okay, basic means lose the electron. Now another properties I am telling you, reactivity towards the halogen. Reactivity towards the halogen. Elements of group 16 form a large number of halides of the type EX6, EX4, EX2, where E is the an element of the group and X is halogen. Okay, the stability of halides decreases in the order. Fluorine is highest, second is chloride you can tell, third is bromide, last is iodide. Okay, again you listen because question is asked. The stability, which halides are stable? The stability of the halides decreases in the order, means fluoride is most stable. After that chloride, and then bromide, and last is iodide. Means fluoride is highest, iodide is weakest. Amongst hexahalides, especially hexahalides, hexafluorides are the only stable halide. Hexafluoride, remember, fluoride, hexafluorides, F6 I am talking about. Hexafluorides are only stable halides. All hexafluorides are gaseous in nature. Again, important point here. All hexafluorides are gaseous in nature. They have octahedral structure. Wherever hexa will come, their structure will be octahedral. Sulfur hexafluoride SF6 is exceptionally stable for steric region. Okay. Sulfur hexafluoride SF6 is exceptionally stable, very stable due to steric region. Okay. Now, because 6 elements are there, 6 fluoride ions are there, then it will surround, sulfur will be in the middle, and everywhere fluorine will be there. It is surrounded by fluorine. Other elements, reactive elements, can't touch the sulfur. Okay, that's why SF6 is exceptionally stable for steric regions. Now, further I am telling, amongst tetrafluorides, SF4 is a gas. Remember it. Amongst tetrafluoride, SF4 is a gas. Se4, selenium, Se4 is a liquid, and Te4 is a solid. Tellurium means sulfur tetrafluoride is a gas, selenium tetrafluoride is a liquid, and tellurium tetrafluoride is a solid. These fluorides have sp3d hybridization. sp3d, 1s3p 1d, total 5 sp3d hybridization, and thus have trigonal bipyramidal structure. Its structure is trigonal, 3 is over and 2 is bipyramidal. Then that's why it is called trigonal bipyramidal structure, in which one of the equatorial position is occupied by a lone pair of electrons. One of the equatorial position is occupied by a lone pair of electrons. This geometry is also regarded as seesaw geometry. Question is asked, what is the seesaw geometry? SEEC dash saw, SAW, seesaw geometry. Means here equatorial position will have a lone pair of electrons. Okay. And other things, all elements except selenium, exception is selenium, form dichloride and dibromide. Exception is selenium. Selenium will not form dichloride or dibromide. Other elements will form. These dihalides are formed by sp3 hybridization, means total 4, 1s3p, sp3 hybridization, and thus have tetrahedral structure. Wherever 4 orbitals will be there, total S1s3p, total 4. In sp3 total 4 orbitals are there. Then it will form tetrahedral structure. The well-known monohalides are dimeric in nature. Here, well-known monohalides, mono means single, monohalides are dimeric in nature. Examples See, SF was there, but it can form dimer, H2F6. SCl, they are unstable, it is forming S2Cl2. Next is S2Br2, Se2Cl2, Se2Br2. These are dimers. These dimeric halides undergo disproportionation. It will go all you can say dimeric halides like S2F2, S2Cl2, S2Br2, SeCl2, SeBr2. All these dimeric halides undergo disproportionation. As for example, 2SeCl2. 2SeCl2, it will break and it will give two product. And there will be, I can say, selenium in both product, selenium will be there. Then 2SeCl2 will give SeCl4 plus Se. Then in SeCl4, selenium has oxidation number +4, and in Se it is a 0. Then disproportionation means that maybe product 2-3 product may be there of the same element, but oxidation state will be different. Okay. Now one question is asked in the last time telling you, H2S is less acidic than H2Te. Why? Tellurium H2Te. H2S is less acidic than H2Te. Why? Answer I am telling you, due to decrease in bond dissociation enthalpy down the group, acidic character increases. Then tellurium is heavy, it is down, that's why it is more acidic than sulfur. H2S is less acidic than H2Te because tellurium is in down. Then due to decrease in bond dissociation enthalpy down the group, acidic character increases. Then this I have discussed, you can say, properties, chemical properties of group 16 elements. Now I am stopping only here. Next class I will discuss you can say other products like dioxygen. I will discuss about the dioxygen and simple oxides of can say group 16 elements. Thank you.